I'll be right back in a moment. Okay, good morning, everyone. Wherever you are, some people it's not morning. For some people, it's midnight. Well, maybe you should have a coffee or something. All right. Before we start, let's open it up to some questions, just a couple of questions about what's going on. If anyone has any concerns about what is going on in this class, ask now, but not about the material yet.
Okay, so Dick Shant has a question.
Yeah, go ahead.
Yeah, hi. It is a concern about the tutorials. So I just wanted to know, because some of the tutorials got absorbed into some other slots, and
Yeah.
I think I also emailed you about like, because the one I was into got absorbed, and all the other tutorials don't really fit my timing. So I wanted to know if there's any chance the original tutorials might be coming back, because then
Okay,
I might
look, people are panicking about the tutorials. Okay, so we had an emergency, which meant that we lost one of our TAs. I mean, he's still alive, but I mean, we couldn't continue being the TA. That's the point. So we're trying to replace the TA, and we expect to have a replacement soon, within a week or two.
So it's temporary.
So
right?
one or two of the other slots will be opened up, but you have to wait. I cannot give you any more information. It was an unexpected event.
All right, thank you.
Anyone else? No one else has questions? Everyone submitted their assignment? No difficulties?
It looks like everyone's okay.
Okay. All right. I wish I could stop the pop-ups, but that's all right. I wish I could also save the configuration of screens, because I need the screens to be in a certain way. Okay, so today what I'd like to do, I'm going to split the class into two pieces. First, I'm going to finish off the material about maps of sets, and second, I'm going to talk about fields. Fields being the fundamental number systems that we're going to use. Okay, and the second assignment is out, and the questions are about these topics, about finishing up maps and then talking about fields. Okay, so let's start with. So remember that we started talking about maps between the standard sets of n, the first n non-zero natural numbers. So let's continue in that way. So I want to talk about classification of maps. And we can focus our attention on maps between the standard finite sets. Remember that Bm or Bk is just the finite set of k numbers, counting numbers from 1 to k. Okay, so how many maps are there from Bm to Bn? Well, there's m elements in the domain. Each one of them has to be sent somewhere. So for each element in the domain, there are n choices for where it can be sent. So that means that there are you have to make one of n possible choices, and you need to do that m times. So the total number, so the cardinality of the set of such maps is that there's n choices for where the first element should be sent, and then there's another n choices for where the second element should be sent, and you do that m times. So this is n to the power m is the cardinality of the set of possible maps. Okay, now among these maps, okay, what I'd like to kind of draw your attention to is that there are maps which are qualitatively different. So let me take, for example, B2 to B3. How many maps are there? Well, there's exactly 3 times 3. There's exactly 9 such maps. So let me draw them all here. Okay, so what do these maps look like from B2 to B3? Well, one of them would be kind of the simplest one I can think of is where both 1 and 2, by the way, so the way that I'm drawing things is using our convention where we kind of label things in the conventional order. So 1, 2, 1, 2, 3. So this is the map that takes 1 and 2 both to 1. Okay, on the other hand, it could be that 1 is sent to 1 and 2 is sent to 2. Or 1 is sent to 1 and 2 is sent to 3. These are all of the maps for which 1, the choice that you made for where to send 1 is that it is sent to 1. Okay, and then you make the 3 possible choices for where 2 is sent. And of course, the same pattern holds. 1 could be sent to 2. If 1 is sent to 2, there are 3 possibilities for where 2 is sent. There, there, and there. And then if 1 is sent to 3, then 2 could be sent to 1, 2, or 3. Okay, so here we have a picture of all possible maps from B2 to B3. Is that clear? Anyone have a question about what I've just listed here? Okay, if we take a look at this, we see right away this one is not injective. This one is injective. This one is injective. This one is injective. This one's not injective. Okay, so on. So what this shows you is that there are some maps that are qualitatively different from others. This one, for example, is quite different from these two. These two are kind of similar. And even this one is similar to this one because we have injectivity. 1 is sent to 2, 2 is sent to 1. Okay, and remember that there's nothing intrinsically ordered about sets. So for example, this one here looks different qualitatively than this one, But the reason this one looks different from this one is that the order is exchanged. But remember that order is not a fundamental property of sets. So really this map and this map are kind of similar, I would say. The ones that are different are the ones like this, which are not injective. Okay, so there are essentially two types. The type where we have collision and the type where we don't. Okay, and these types you could call them classes. Okay. And this is what I mean by classification, is putting them into classes. It's really a partition on the set of maps. So what I'd like to do is I would like to say that somehow these are in one class and the rest are in another class. Okay, so how are we going to classify these? Well, we need a definition which will be able to tell the difference between the two types. Okay, so for example, why do I say that this one here is similar to this one here? Well, the reason is that it has the same behavior, that both of the points in the domain are sent to a single point. That's true for this one, and this one. The problem is that this single point that they're sent to is different in these three cases. Okay, but what I could do is I could say that we will consider two maps to be similar. We're going to define similarity of maps. Okay, and the definition is going to work like this. We're going to say that two maps are similar when they can be made equal to each other upon relabeling of the domain or the codomain. So in other words, if I relabel, so suppose that I look at, let's look at this map F and let's look at this map G. Okay, so F, actually, let me just grab them. So if I take F, and if I take G, okay, and if I look at these, they're obviously not the same map. However, if I wanted to make them equal, what I could do is I could compose G with a relabeling of the codomain. So how do I relabel the codomain? Okay, so what I do is I take another copy of the codomain. So this is B3 and this is B3. Okay, and then what I'm going to do is take a symmetry of the codomain. So a symmetry of B3, or in other words, a bijection from B3 to itself. So what I'll do is I'll relabel by sending 2 to 1. And then I need to do something with 1 and 3. You can choose what to do with it. You can't send it to 1 because we need it to be a bijection. And then 3 can go like this. This is one possible choice of relabeling. So this is a relabeling, or another way to call it is a symmetry or a bijection from B3 to itself. Okay, let me call this alpha. Okay, and if I compose G with alpha, so if I first apply G and then alpha, you can see that this is equal to F. So this here is my relabeling of the codomain. Okay. And as a result of this equation, I would say that F and G are similar. Okay, so the definition, this is just inspiration for the definition. We'll say that F is similar to G when we can find relabelings alpha and beta of the domain and the codomain such that alpha, G, beta, oops, sorry, of the problem is it can be confusing about which one is which, of the codomain and domain, such that alpha, G, beta is equal to F. And let me just make it a little bit more precise. I'll just say what we're starting with. Let F and G be maps X to Y. But actually, just because I don't want to get too far afield, let's just fix the domain and the codomain to be the standard sets. Okay, so the basic idea is that we're going to consider maps like this, maps from Bm to Bn. Okay, and we're going to say that they are similar when, upon relabeling, they are exactly the same. Okay, so here, for example, you can see, just as an example, for if we have this map and if we have this map, let's call this one F and this one G. Okay, then there's choices. There are many choices, or there's a few different ways that we could make G equivalent to F or G similar to F. For example, one option would be to relabel the codomain like we did before. So if we switch 1 and 2 and leave 3 alone, okay, so this would be G alpha, and that is equal to F. Okay, but another possibility would be to relabel the domain with beta. Okay, and we would have G composed beta is also equal to F. Okay, so both of these options show that G is similar to F. Okay, so let me just make a note, just for your general education. So this similarity, similarity relation is an example of what's called an equivalence relation. Okay, the idea of equivalence relation is really important and will show up in all your math classes. So an equivalence relation is is a notion of similarity that you have to define on a given set, which basically breaks up the set into special subsets. Okay, and these subsets contain elements which we consider to be similar. And there's many different types of equivalence relation. So for an equivalence relation on a set, it must satisfy some axioms. So first of all, every element of the set must be equivalent to itself. If X is equivalent to Y, we need it to also be the case that Y is equivalent to X. And finally, if X is equivalent to Y and Y is equivalent to Z, then X must be equivalent to Z. This is for all X, Y, Z in S cross S cross S. Okay, so this axiom is called reflexivity. This one is called symmetric. And this one is called transitivity. Transitive, like if X is equivalent to Y and Y is equivalent to Z, then we can transit through Y and go directly from X to Z. X is equivalent to Z. Okay, so what's the function of an equivalence relation? Well, we've kind of seen this before. The function of an equivalence relation is that it basically breaks up your set into subsets. And that's what is that? That's a partition. So equivalence relations are essentially exactly the same type of thing as partitions. Okay, so here we've got a set. It's a set of 9 elements. It's the set of maps from B2 to B3. Okay, and that set of 9 elements has been partitioned into one set of 3 elements and another set of 6 elements. All of the elements of the purple set are equivalent to each other, or similar to each other in the terminology that we introduced. And all the 3 elements in the yellow set are also similar to each other. Okay, here's a little exercise. Prove that similarity of maps is an equivalence relation. So that just means you need to prove that it satisfies these axioms. Okay, any questions so far?
So Charlie has a question.
Yeah, go ahead.
Yeah, just for going back just a tiny bit to where you say, what is it? Alpha composed G is equal to F, or G composed beta is equal to F.
Yeah.
When you do alpha composed G composed beta, that isn't equal to F because it's just like you're sending it back to the initial G values, I believe. Right?
That's right. Yeah. If you were interested in computing, let's say, beta G alpha, this is, if you just look at it, right, it says it sends 1 to 1 and 2 to 2. So it's basically just G again.
Yeah. And so then when you have the where it says we can find relabelings A, alpha and beta of codomain and domain such that alpha composed G composed beta is equal to
Yes.
F. Oh, I see what that means. Okay, now I do. So it's like alpha composed G is equal to F, and then G composed beta.
No. Sorry. Don't get sorry. I maybe this is a little bit confusing. So, okay, 1 second. Could you mute yourself?
Oh yeah, sorry.
Okay, so I don't want this to be confusing. Okay, so you have two choices here. These are possible choices. Okay, so I just gave this, in this case, we use a non-trivial relabeling of the codomain, but a trivial relabeling of the domain. So we don't relabel the domain. Whereas in this case, we relabel the domain, but we do nothing to the codomain. And in both these cases, we obtain F. So if you were asked to prove that G is equivalent to F, there's many different ways of demonstrating that. You could either use this pair of relabelings, or this pair of relabelings, or some other pair of relabelings. Is that clear?
Yeah, thanks. Also, sorry for the jackhammer in the background.
It's okay. Anything else?
So Jay has a question.
Go ahead.
Okay, so for this relabeling, you had mentioned that something is a group. So is the group the mapping from, say, set, just whatever our set is, to the relabeling, essentially, the map onto itself, right? That's the group per se.
So when you say group, right? Group is something that has a composition, has a multiplication, right? So maps from BM to BN do not form a group because you can't compose one of these maps with another one of these maps because the domain and the codomain don't agree. But if we were talking about maps from BM to itself or from BN to itself, those two sets of maps, they form groups.
Okay.
One of them is the group of permutations of 2 elements, and the other one is the group of permutations on 3 elements. So what we see here is that beta is an element of the group of symmetries of 2 elements, and alpha is an element of the group of symmetries of 3 elements. Beta and alpha are elements of 2 separate groups.
Okay.
Okay, let me okay, let me do another example. Suppose that I had B6 going to B4. And suppose that I did it like this, suppose. suppose this was my map, F. Okay, then what would the matrix of this map be? Well, remember that the way that we write the matrix is that we basically draw the graph of the map. So we put the domain as the x-axis and the codomain as the y-axis, except that the y-axis is going down, right? So we're going to have basically, I'm going to need to know, where does 1 get sent, 2, 3, 4, 5, and 6? Where do they get sent? So, so I put my domain on the top axis, on the x-axis, and I put the codomain on the y-axis. So where does 1 get sent? 1 gets sent to 2. And 2 gets sent to 4. And 3, 5, and 6 are all getting sent to 3. And 4 is getting sent to 4. One, two, three, 4. 4 and 2 should be sent to 4. Okay, good. I'm doing this in order to get you used to matrices later on, but this is a perfectly good use of matrices. So this is the matrix of this map from B6 to B4. It's a 4x6 matrix with binary numbers, with logical numbers. You know, like this is saying that 3 is sent to 3. So it's like a truth value of 1, that 3 is sent to 3. Hopefully it's true. 1, 2, 3. 3 is sent to 1, 2, 3. Okay, so I just want to indicate that this is something that routing, like old-fashioned routing, is all based on this correspondence, right? So let's say that you have you have some musical inputs coming in. There's 6 musical inputs, and then you need to reroute them to 4 outputs, like 4 speaker outputs, let's say, right? So one way to do it would be to have a bunch of wires, and you just connect the wires exactly like this, so that the 6 instruments can find 4 speakers in whatever the configuration you want. Okay, but another way of doing it would be to take your 6 instruments and just plug them in order, 1, 2, 3, 4, 5, 6. Okay, and take your 4 speakers and plug them in order, right? And make that like a permanent attachment that you never have to worry about. So everything is organized. The 6 elements, the 6 musical instruments are in order, plugged into this square board, right? Just imagine that you had like a board, a rectangular board with 6 plugs along the top and 4 plugs along the side. You plug in the instruments on the top and you plug in the speakers on the side, and then you never change the wiring, right? And then what you come in with is you come in with this matrix, right, which tells you which connections to make. So you plug in, 6, metal rods, right, which makes a connection between 1 and 2, between 2 and 4, 3 and 3, 4 and 4, etc. Right. So you can imagine that you can kind of manufacture, some kind of plate that plugs in to your board that has exactly this configuration of connections. And that would be, a set way of connecting your instruments to the speakers. And then you could have another matrix, another board, another plate for another occasion, which comes in and you plug it into the board, and it makes a different configuration of connections, right? These are, this is like the old-fashioned way of having different configurations, right? You can just make one connection board and then put the routing plug in to tell which connections you want to make. Anyway, what happens if I relabel? So if I start to do relabeling, I just want to indicate, there's an assumed label here because I'm dealing with B6, which is just the numbers from 1 to 6. These points are actually labeled with numerical values. Okay, but suppose that I wanted to simplify this map. Suppose that I wanted to, it looks kind of complicated. What I'm claiming is that I can simplify it by relabeling. So let's see what kind of relabeling I want. I'm going to try to get the most collisions. I want to separate them out and put them first. So you see how here 3, 5, and 6 are all sent to 3. What I'm going to do is relabel the codomain so that happens first. So that goes to 1. So I'm going to take 3 and map it to 1. Okay, this is the codomain I gave the name alpha to, right? Codomain relabeling. Yeah. So I'll call this alpha. Then the next one, you see how 2 and 4 are both sent to 4. So there's a collision of values there. I'll put that second. Okay, and then I get a single value for 2, so I'll put that third. And then there's a value which is not taken, namely 1. I'll put that one last. Okay, so this is my permutation of 1, 2, 3, 4. Okay, and if I do that, this corresponds to this codomain relabeling. Okay, it corresponds to relabeling, rearranging the rows. You see, because 1 was originally sent to 2, but now I'm going to send 2 to 3, right? So that means that this row, right, which is basically telling you whether a certain input is being sent to 2, right, that will now become, anything that is sent to 2 is now going to be sent to 3. So this row needs to be moved down 1. So, so I'll put it down here. So, sorry, 1, 2, 3, 4. I just want to do this carefully so that you, okay, so that's now my new row 3, because 2 is sent to 3. 3 is sent to 1. So the third row is going to have to go upstairs. So it'll be 0, 0, 1, 0, 1, 1. And so that's 3 is sent to 1. 4 is sent to 2. So it's the fourth row that I need to replicate in the second row here, 0, 1, 0, 1, 0, 0. And it's 1 that is sent to 4. So I'll have a row of zeros because nothing takes that value. Okay, so this is the matrix now for F alpha. This is the matrix for F. Actually, let me just give this a notation. So I'll call this matrix is M of F, the matrix of F. And this one is the matrix of alpha composed F, the relabeling of the codomain. Okay, so right. Okay, so now I want to simplify it further because if we look at this one here, then we see that 3, 5, and 6 are all being sent to 1. So we have a group of 3 points which are being sent to 1. Okay. And those 3 points are labeled 3, 5, and 6. I want to simplify it. So I want to relabel the domain now so that those 3 which are sent to 1 are actually first, 1, 2, 3. So I want to relabel my domain to put things in better order. So I'm going to let 1, 2, and 3 go to the 3 points that are sent to 1. So those are 3, 5, and 6. So this will go to 3. This will go to 5. And this will go to 6. Okay. And what that is guaranteeing now is that 1, 2, and 3 are all sent to 1. Oops, sorry. Okay, and then we look at the next one. So remember that if we look here, what is being sent to 2 is a pair of elements, the element 2 and the element 4. So those elements which are labeled 2 and 4, I want those to come next. So these 2 elements are now going to go to 2 and 4. And that means that elements 4 and 5 are going to be sent to 2. And finally, the element 6 has no choice. It has to go to 1. And then 1 is being sent to 3. Okay, so this here is the matrix of alpha, F, beta, where beta is defined like this. And what we see is that the matrix has a very nice organized format. 1, 2, and 3 are sent to 1, 4 and 5 are sent to 2, and 6 is sent to 3. Okay, and if I was to draw this, this new map, alpha composed F composed beta, sorry. Okay, what do you see? It would be that the first 3 are sent to 1, the next 2 are sent to 2, and the last is sent to 3. Okay, so if you compare the original function, the original map, with this relabeled map, you see that it appears to be a lot simpler, and it demonstrates the partition that we get. Look at the partition. You can see that we have a partition of 3, a partition of 2, and a subset of a size 2 and a subset of size 1. So we get, we can just visually see the partition of the domain by preimages. Okay, so I'm not going to bother going into great detail about this, but basically the procedure that I outlined here it leads to the following very easy theorem, and that is by relabeling the domain and codomain, any map Bm to Bn may be so is similar to one in standard form, where I'll just indicate that by drawing the matrix. And the matrix is that you have a certain number of ones Okay, there's a certain number of them. Let's call it M1. And then you have a certain number of ones on the next line and near and next to it. So I'll put put the walls here. And so this is M2, and this is MK. Okay, where M1 plus MK is a partition. Okay, and we can also make it even more organized by making sure that the biggest ones go first. So M1 is bigger than or equal to M2, bigger than or equal to all the way down to MK. And everything else that I haven't written out is a bunch of zeros. Okay, so here we see a 4x6 matrix, which is in the standard form. Okay, so this is what I meant by classifying maps. That every map, no matter how complicated, like for example this initial map, right? By relabeling the domain and the codomain, it is possible to put the map into a standard form where you just have the partition of the domain in decreasing order or non-increasing order. And then each partition set is sent to the corresponding point in order on the codomain side. And that's what the matrix will look like. So this is a really simple classification result. It just tells you what every possible map from Bm to Bn looks like, what it qualitatively looks like. Okay, any questions about that?
So Dikshant has a question.
Yeah.
Oh, I had a question about the previous, when you went to the very first time when you were graphing this. I just wanted to know, when you relabel, when you're doing, shouldn't the codomain and domain be same for a composition to be possible? But I think like
Sorry,
when
where are you, what are you, can you please indicate what you're looking at? Which composition are you talking about?
go to the very first composition when you started this with G of F or F of G, like on the previous page.
Here?
Like the one above. Yeah, just the previous page again, F and G are similar. Yeah,
Yes.
so when we have B3, so over here B3.
Okay, so just one second.
Yeah.
So G is a map from B2 to B3.
Mm-hmm.
And alpha is a map from B3 to B3. Okay,
Yeah.
so we have a map going from one set X to a set Y, and then we have another map going from that same Y to a set Z. That is what you need in order to be able to compose. You need to take elements here and map them here, and then apply alpha to map them here.
Right. So it doesn't really matter that the original from B2, we have nothing going to B3, but in the from B3 to B3, like at the third element in the set B3, that has something going from B3 to B3, but not from B2 to B3 going to the third point.
So the only thing you care about when you compose two maps is where are the points of the domain sent? Where is 1 sent and where is 2 sent? That is the domain. So if you know where 1 is sent and if you know where 2 is sent, then you're done.
Yeah, okay, I think I get
You
it.
may wonder, oh, but nothing is sent to 3. Well, I mean, you can only do so much. When you go trick-or-treating, I don't know if you have done that, you cannot go to every house, but who cares? All that you care about is what the candy is that goes into your pail. That's a good analogy, but you have to think about it for a while. Okay, so this is okay. So I just want to point out I didn't say something which I should have said. So here, what I started off with a complicated map which had this complicated matrix. Okay, then I relabeled the codomain, and because the rows are correlated with the codomain 1, 2, 3, 4, right? Permuting the codomain, what it does is it effectively permutes the rows of this matrix, as you could see here, right? The third row suddenly becomes the first row. The second row becomes the third row because 2 is being sent to 3. Okay, so but once I have this matrix, right? The thing that I wanted to do was I wanted 3, 5, and 6 to all go at the front because 3, 5, and 6 are being sent to 1. So I wanted to put these in the first positions in the domain. So what I did was I relabeled the domain. Now, it's the columns are the ones that are correlated with the domain because there's one column for every element of the domain. So when I do this relabeling of the domain, what I'm really doing is I'm reordering the columns. I'm shuffling the columns. Okay, and what I did was I put the third column in first position, the fifth column in second position, and the sixth column in third position. So these 3 columns now appear in the front. So I just want to point out, this is a very important fact for later on, is that alpha gives rise to a row operations, row switching, or row permutations. And beta gives rise to column permutations. And so you could think of the problem just from the point of view of the matrix. You could say, okay, starting with this matrix, can I put it into the standard form by just doing permutations of the rows and permutations of the columns? Okay, so you could organize it that way. You could definitely put the heaviest row, the row that has the most ones, you put that one at the top, switch that, and then you put the second heaviest row next to it, right? So you arrange the rows in decreasing weight, okay, and then you arrange the columns the way you want, so that you achieve this format. Okay, this is called so. This is an algorithm. I've presented to you an algorithm. I didn't write it out step by step, just because later on we're going to see a very similar algorithm, which I will write out step by step. But I just wanted you to get comfortable with this idea that by relabeling the domain and by relabeling the codomain, you get two types of operations on the matrix. One of them changes the rows and the other one changes the columns. And you need to know which one is which. Okay. Now, before I go on to the second part, and we're going to have a break, I just want to talk, I want to say something very important about a special case. So there's a very special case that occurs, which is when you study maps and I'm going to focus on bijections from X to itself. Okay. So for example, I'm going to look at Bn mapping to Bn. Okay. So this is a very special case. It's a very important special case. Okay. And it's not just because n is equal to n. Okay. So let me explain what I mean. So there's a very important idea here that happens when they are the same that doesn't occur elsewhere. So okay, so labeling a self map. So I need to explain this idea. Okay, so suppose that I have a map. Let's say I have a map like this. From a set of three elements, A, B, and C, to itself. And suppose that it looks like this. A is sent to B, B is sent to C, and C is sent to A. So this is a bijection from ABC to itself. Okay, there's a different phenomenon that happens when it comes to labeling. Okay, because so the key idea is that once we choose a labeling of the domain, so, and by that I mean, so what is a labeling of this domain? The domain is a set of three letters, and I want to label it with numbers. So what I want is there's three of them. So I want a labeling to go from this set A, B, C to B3, a bijection. This is what I mean by a label. Labeling, what I mean is that every element of the set is assigned a unique number, right? A classifier that tells you which number it is. Okay, so once we choose a labeling of the domain, this automatically gives a label for the codomain. Okay, this did not happen before. You see, here I had my domain and I had my codomain, and if I choose a labeling of the codomain, it certainly does not tell you what the labeling of the domain should be, because the domain and the codomain are different sets. But when the domain and the codomain are the same set, then you only have the ability of choosing once. Once you've chosen the labeling for the domain, you've already labeled the codomain. So there's not two, you do not have two independent choices. So i.e., we do not have two independent choices. of label. So we have less freedom. Okay, what do I mean by that? So think about it like this, that in the original problem, I started with some complicated map and I tried to simplify it. I tried to find a similar map. Oh, there's people in the waiting room. Do you see Syed, do you see when people show up in the waiting room?
I do see them, but I don't see anyone right now.
Oh, maybe it's just the pop-ups for me don't get destroyed. Okay, so what I did was I took this complicated map and I tried to find a similar map which was simpler in appearance, right? So I relabeled the codomain, and when I did that, it still wasn't simple enough. So I used further freedom to simplify it even more. So I said, whoa, but I'm free to relabel the domain in addition to the codomain. So I'm going to make a choice which is advantageous for me, and I'm going to put it all into this very nice organized format. Okay, but for example, in this case, let me grab this. Actually, I want the labels too. Okay, so if I try to simplify this, let's say that I said, you know, A is sent to B, but I wanted to, I want to send it back to A, suppose. So I'm going to relabel the codomain by sending B to A to C, and C to B. Okay. Oh, I'm sorry, and I sorry, I said that I was relabeling it, but I don't mean I don't mean just having a bijection. I mean actually labeling it with numbers. So I'm going to send B to 1, C to 2, and A to 3. Okay, but now I've automatically labeled A, B, and C on the left side as well. So if I have 1, 2, and 3, right, then A is sent to 3, B is sent to 1, and C is sent to 2 according to my relabeling. So let me give this set a name. So let me call A, B, C, S. So we have S mapping to B3, and we have S mapping also to B3. And then we have our map F, which is a bijection from S to S. So the point is that I labeled S, okay, but by labeling S, I label both the domain and the codomain, and so I get a map from B3 to B3 with a single choice. Just by choosing alpha, I get a map from B3 to B3. And this map, what is it? Well, first I need to reverse alpha. So if I want to go from here to here, I need to go alpha inverse. Okay. Then I need to compose that. That's a circle composition with F. And then I need to compose that with alpha. Okay, so by choosing the labeling alpha, which goes from S to B3, we obtain the map F composed alpha inverse composed alpha, which goes from B3 to B3. And if we work that out, 1, 2, 3, 1, 2, 3, then you see that what I get is that 1 is going to be sent to 2. 2 is sent to C. C is sent to A is sent to 3. So 2 is sent to 3. And 3 is sent to A, is sent to B, is sent to 1. So this is my labeled map, alpha F alpha inverse. Okay, but there's no way around it. So if I try to relabel, so if we relabel, okay, this takes effect on both the domain and the codomain. Okay, so just to give you an example, I could take this map, right, and I could do something like this, let's say. Okay, so I could relabel the codomain like this, and if I relabel the codomain like this, then the domain must also be done in the opposite way. So this is going this way, and I just use the same relabeling, but in the but on the domain, right? And if I compute this, then I'm just going to get 1 is sent to 3, 2 is sent to 1, and 3 is sent to 2. Okay, so notice that this is another representation. It's another similar map to the original map here, or to this map here. This is a map from 1, 2, 3 to 1, 2, 3. So, so these two maps are similar. They're not exactly the same map. Okay, here 1 is sent to 2 and 2 is sent to 3. This is 1 is sent to 2, 1 is sent to 3 and 2 is sent to 1. These two maps are similar, but they are not the same map. But the point is that I cannot, we cannot relabel to obtain this map. You see, the identity map, it is not possible to relabel this to give the identity map. Okay, when we're dealing with the same set being sent to the same set, because once you relabel the codomain, the relabeling of the domain is fixed, you know, is forced. So we cannot relabel to obtain the identity map unless we allow independent relabeling of the domain and codomain. Okay, so what this means is that we have two different equivalence relations. So so we have two equivalence relations. Okay, so in the first case, the first one that I explained is that for maps, let's say f x to y, where the domain and the codomain are different, we say that f and f prime are similar when there exists relabeling of the codomain and a relabeling of the domain with f prime being given by alpha f beta. And then the second thing is for maps f from a set to itself, we say that f and f prime. So here, there is no standard terminology for what I'm talking about here. So this, some people might call this similar as well, even though it's a different notion of similarity. So for me, for today, I'm just going to call it conjugate instead. So f and f prime are conjugate if there exists a bijection alpha from x to itself. I'm going to use this symbol. This is the isomorphism symbol for bijection. So this just means bijection. Okay. If there is a bijection from x to itself such that f prime is alpha f alpha inverse. Okay, these are two different notions which are both very useful, each one of them. Okay, and one of them is more free than the other. So this one has a lot more freedom because you can choose alpha and beta. And this one has less freedom. You only can choose alpha. Okay, and it only applies when the maps are from the set to itself. Okay, and what I'm claiming is that there is no way here to relabel the domain and the codomain. There's no way to choose the relabeling of the domain so that when I apply that relabeling to both sets, I get the identity map. And the reason is that, you know, what this map is doing is that it's really permuting the elements of the set. It's taking, you know, A is being moved to B. And so you can tell that A is not moved to itself, is not mapped to itself. A is not a fixed point of this map. And so that's why, you know, it's clear that you cannot relabel, you cannot obtain a fixed point just by relabeling things. Relabeling things is not really changing the nature of the map. It's just changing the labeling ABC to 1, 2, 3. Okay. So it's obvious that I'm not going to be able to relabel and get a situation where A is being sent to itself. Okay, and so just to give you the last piece of information about these bijections from the set to itself, when you classify bijections from Bn to Bn up to conjugation. So that's what I mean here. I want to consider two bijections f and f prime to be conjugate when there's an alpha which satisfies this condition. Okay, you need some simple ideas which I explained in the assignment. So the first thing is that the idea of a fixed point is x is a point in the domain. Well, let me just, so a fixed point of, this is what I explained in the assignment, a fixed point of a map from x to itself is a point inside the set with f of x is equal to x. Okay, so notice that the idea of a fixed point cannot even exist when the domain and the codomain are different. We can't even have a fixed point. It doesn't even make sense. Okay, but there's something that goes beyond fixed point, and it's a fixed point is a special case, and it's called a cycle. So a cycle of this map is a subset of the form where you have an element and then you apply the map to that element, but that is not x, so it's not a fixed point, then you apply the map to the result again. So I'm iterating now the application of the map to that element. And I just apply the map again and again. Okay, and that set is yeah, so I mean it's conceivable that it could continue forever if the set was infinite, but if we focus on finite sets, then eventually this thing must come back to itself. And that's why this is called a cycle. So this is what we mean by a cycle. And let me just give an example. So you can see that it's almost like a fixed point. It's like a subset that's fixed. It's sent to itself. It's just that all the elements in the subset are just shifted over by applying the map. So let me just give an example. So suppose that we had a map from B4 to B4, which was taking, let's say, 1 to 3, 2 to 2, 3 to 4, and 1 to 1. 4 to 1. Okay, so here it's important that I am mapping a set to itself. So this is from B4 to B4. So when you look at such a map, you can ask about the fixed point. So here we see that there is one fixed point. So 2 is a fixed point because f of 2 is equal to 2. Okay, and then you might ask, well, okay, is 1 a fixed point? Well, 1 is not a fixed point because if I apply f to 1, I get 3. This is f applied to 1. And then if I apply f again, it will be sent to 4. So this 4 is equal to f of 3, right? You see, I've applied the map again. And then if I apply the map again, f of 4 is equal to 1. Okay, so I'm already back to a point that if it's already in the set and I don't even need to list it because listing it again isn't going to help anyone. So that's the set. So this is a cycle of length 3. Okay. So whenever you have a cycle, so in a cycle, we can label x by the number 1. We can label f of x by the label 2, and so on. So we can label every time we apply x, apply the map, we can increase the label. And then what we would get is a map which sends 1 to 2, 2 to 3, okay, and so on up to k, and then k would be sent back to 1. So we get, that's the reason why it's called a cycle. Okay, so this would be the map F. Okay, and the matrix of such a cycle, if F, let's say Bn, or let's say Bk to Bk is a cycle labeled as above, has a cycle labeled as above, then the matrix of F would be like this. So 1 would be sent to 2, 2 would be sent to 3. Okay, and so on. Okay, and the last one, K, would be sent back to 1. Oops, sorry. Okay, so you have a matrix which has, it's a square matrix because I'm mapping a set to itself. So the domain and the codomain has the same size. So it's a square. And then there's ones just beneath the diagonal of the square. And then there's a single 1 in the top right corner. And this is what a cycle looks like. 1 is being sent to the next number. 2 is being sent to 3. 3 is being sent to 4. You know, K minus 1 is being sent to K, and then K is being sent to 1. Okay, and then the classification theorem is that any bijective self map is basically a collection of these cyclic pieces. Okay, and a cycle of length 1 is equal to, is just a fixed point. Okay, so let me so just quickly, because you're probably going to see this in other classes. This is why elements of the group Sn, these are bijections from Bn to itself, are usually written in what's called cycle notation. Okay, so let me just demonstrate that with some examples, and then I'll be done with this section. So if we have the trivial map from 1, 2, 3 to 1, 2, 3, so the identity map, we would write that in cycle notation as just 1. Okay, if we had this map, okay, we see that 1, nothing happens to 1, but 2 is sent to 3 and 3 is sent to 2. So that means that I have a cycle of length 2. 2 goes to 3, 3 goes to 2, 2 goes to 3, 3 goes to 2. And we denote that in this way. We put, we just put parentheses and just list the cycle. And it's understood that when you get to the end, you have to go back to the beginning. So 2 is sent to 3 and 3 is sent to 2. Okay, so if I do this map, oops, sorry, I just want to draw them in red. So if I look at this map from 1, 2, 3 to 1, 2, 3, then I know that 1 is sent to 2, 2 is sent to 3, and 3 is sent to 1. So we would write it in cycle notation like that. On the other hand, there's another possibility, which is that 1 might be sent to 3. Oops. 2 might be sent to 1, and 3 might be sent to 2, another bijection from 1 to 3 to itself. Okay, and this would be a different cycle because 1 is sent to 3 and 3 is sent to 2. Okay, and so anyway, the point is that this cycle notation is used a lot in group theory. It's a shorthand way of writing this matrix, and it's a shorthand way of writing this or this, right? These are all different ways of representing these maps. Okay, I want to take some questions. So, but I also want to take a break. So let's say, so I'll take some questions now, but we'll start again at 12:40. Normally I like to take a real break, but let me make an exception today. I'll just take questions for 10 minutes and then we'll start the lecture again. So feel free to take a break for the next 10 minutes.
Okay, so Chu has a question.
Hi, Prof.
Hi.
So my question is kind of going back to the 3 conditions of equivalence relation.
Yeah.
Yeah, like, why do we need a transitive one? Because I believe they can be deduced from the second symmetric one.
No, that's not the case. No, you have to think about why that is, but it certainly does not follow from the second one. Yeah, so for example, yeah. Yeah, it's just the problem is that you are familiar with many different equivalence relations, but you may not be used to seeing relations which are not transitive. So there's many relations that are not transitive, like for example, if I am in physical contact with my if I have had physical contact with my pet cat, which I don't have, I don't actually have a pet cat, so this is what's called a hypothetical situation. So, and if my pet cat has touched a mouse, that does not mean that I have touched the mouse.
Okay, I get it. Thank you.
Okay, that was easy. Okay.
Okay,
so if I touch the pet cat has touched me, right? So it is symmetric. If I can touch myself, the cat can touch itself. Right?
Okay.
It is in physical contact with itself. But the problem is that I cannot, just because the cat touched something doesn't mean that I touched it. So yeah, that's the problem with non-transitive relations.
Thank you.
The problem is that COVID is quite transitive. That's the reason that the reason that we're here today. It's because it is transitive. If I touch someone that has COVID, there's a good chance, and if they touch someone that's COVID, then I have to be worried that maybe I have COVID, right? But even that is not perfectly transitive. See, and that's a good example. Like if it was, yeah. Anyway, other questions?
Yeah, so Jay has a question.
Go ahead.
Yeah, so when we had the mapping from B6 to B4, we were able to relabel both the domain and the codomain, right? It was what you were saying about the plug door, essentially, right?
Yeah, we allow ourselves to relabel to give a
Right.
labeling to the domain and to the codomain.
Right. So I think my confusion was if you do the bijection of some bn onto itself, I think I was kind of confused. So why does that force any relabeling of the codomain to be the same or the inverse?
It doesn't. It does
Okay.
not. That's a good question. So, just because we're mapping from a set to itself, okay, it doesn't mean that we can't just pretend that the sets are different and make two independent choices of the labelings of the set. Okay, but the key point is that if you're taking a bunch of if you're trying to teach a computer how to play a shell game, what is a shell game? A shell game is where you take like a rock or a shell and you put it underneath a cup, and there's 3 cups, and then you move the cups around and you have to try to figure out which cup has the rock underneath it. People usually play this with a cat. You rearrange it quickly, and then you see whether the cat could follow where the rock went, right? So if you're trying to teach a computer how to play a shell game, right, you have 3 elements of your set, the 3 cups, and you want to label them, right, once, right? You want to label them at the beginning, and you want to see what happens to those labels. You do not want to relabel it at the end. That's useless, right? So it's not that you're forced to do it. It's the problem is that, when you're trying to describe a map from a set to itself, there's a more important mathematical problem that occurs, which is how do I classify those maps without forgetting the fact that it's the same set that is the domain and the codomain. In other words, I only want to label it once, and I want to maintain the information that it's the same thing at the beginning and at the end, right? So it's a more difficult problem. It's like saying, can you, I know that you can simplify your map by making all these choices of the domain and the codomain, but can you actually simplify it by making the minimal amount of choices? Namely, you only label it once, and that should be enough. So it's a more difficult mathematical problem that occurs in the case where you're mapping from a set to itself.
I think I sort of see.
So the point is that if you did it by making both choices, you would be doing a special case of the thing I already described. You can, of course, do that special case, but what I was doing here was introducing a new problem. This is a new problem of how to label a self map in a convenient way. And it's a different problem than the one before. You're not forced to use this method. It really depends on which problem you're trying to solve.
Okay.
Okay, so Shuji has a question.
Yeah, I have question regarding the similarity of the maps. So in the definition of the similarity, there is two maps, alpha and beta. But we've previously talked about the possibility to show 2 maps are similar. So one of the alpha or beta must be a trivial one. Is that?
No, I picked, I mean, there's nothing in the definition that says that alpha or beta must be trivial. I just picked 2 examples where this one beta is trivial and this one alpha prime is trivial, but there's no reason for those maps to be trivial. You could have chosen a different.
Yeah, I could have chosen a different, but So,
for example, here, this is what I did here. I have a complicated map. I chose a bijection of the codomain. I chose a bijection of the domain.
Yes.
And I simplified the map into this map. So this map is similar to this map. Exactly. This is an example where beta and alpha are both non-trivial.
Yeah, this is an example. So to show 2 maps are similar, is it possible that we just use alpha or beta? Like we don't need to use both two of them.
Well, I gave an example where F and G are similar
Yes.
by taking beta to be the identity map and alpha to be a non-trivial map.
Yeah, exactly. So
that is an example satisfying your question.
Yeah. So like, does every map satisfy that?
Good question. Think about that. So what does that mean? So you're asking, if F and G are similar, is it possible to show that they are similar by using only alpha and not using beta?
Yeah, exactly.
Well, good, good question. Try to figure it out.
Okay. Thank you.
When you have a question like that about why a definition is the way it is, right?
Yeah.
It's probably the case that the definition is needed. So the nature of the definition is probably not redundant. So you have to figure out why. So you should guess that the answer to your question is no, that it's not possible. Because if it was always possible, the definition would probably be different the way it is.
Yeah.
Right?
Okay.
So you need to figure out why it is not possible to do that all the time.
Okay. Yeah. Let me think about it after.
Yeah.
Thank you.
Okay. Any other, is there an urgent question or can I continue?
So it looks like there's 4 questions in the, Omar has the next question.
Okay, Omar, go ahead. You're the last for now.
Yeah, hello, Professor.
Hi.
Yeah, quick question. Actually, what's the notation for when there's multiple cycles in one set, in one map?
Yeah, good question. So if you have, let's say, this is 2 cycles. So you would write 1, 2, 3, 4.
Oh, that's it? No plus, no anything?
No.
All right, then. Thank you.
And if you had, this would be 1, 2, 3, 4.
So we do not, we don't mention.
You don't even bother writing the fixed points. It's assumed that the fixed points are fixed.
I see.
Okay, so now in the last 15 minutes, okay, I just want to introduce, we need to go beyond sets. So beyond sets. And the way that we go beyond sets is that we equip a set with an algebraic structure. Okay. So algebraic structure, well, I don't want to give a formal definition of what an algebraic structure is. You can look on Wikipedia. It has some very nice articles about it, and it's related to the Bourbaki school. It's a relatively modern idea, but I'm just going to give you a feeling for it. So what you are supposed to do is you're supposed to start with at least one non-empty set. Okay. You may have more, and when we learn vector spaces, we will have more. We're going to have 2 sets. Typically, we don't have that many. It's either 1 or 2 for most algebraic structures. And then we're going to have some kind of operation on A. So initially, so the one that we usually start with is a binary operation. And that means that it takes 2 inputs in A, and it has 1 output. So it takes two things, combines them, and produces an output. Okay, but you could have a collection of operations. Of finite arity. So in other words, instead of binary, it could be, that's two arity, like arity 2. It means that it has two inputs, but it could have three inputs, let's say. It could be a ternary operation, could be from A cross A cross A to A, or it could be unary, which means that it goes from A to A. Okay, or it could be zero-ary, okay, which is a map from a one-pointed set, a set that has one element to A. In other words, an element of A. Okay, so these are all examples of operations. You could have an operation that has three inputs and one output. You could have an operation that has two inputs and one output, or one input and one output, or zero inputs and one output. If you have zero inputs and one output, that's nothing but an element in A. So this is zero inputs. Okay. And then with these operations, you have certain laws, certain identities that you assume hold between the operations. These are sometimes called the axioms. Okay, so instead of spending too long on the general idea, let me just start by building it up. So example number 1. Okay, this is called a magma. Something that you will likely never hear again except for today. Okay, it is a set with a binary operation. And no laws. Okay, and you can think of it as a picture like this, that we have two inputs going to one output. So this is A and B are the inputs. They combine together almost like it was water flowing from the hot and from the cold. They get combined inside the faucet and then they get shot out from the faucet. A star B. Okay, and I draw the arrows down almost like gravity is pulling everything down. Okay, is that clear? That's your first example. It's called a magma. So it's just any binary operation. So for example, you could take the real numbers and you could take x star y is equal to x y cubed plus 3x minus y. There you go. That's a binary operation. Not a very interesting binary operation, but it is a binary operation. It takes two inputs and gives one output. Okay, so we don't really care too much about magma because magma is like too loose. It's not, they don't occur, they're not something that we should spend too much time studying. Example number 2. A semigroup. Okay, what's a semigroup? Well, it's a magma. A magma. Okay, but the binary operation satisfies the all-important law of associativity. Okay, and the associative law is like this: that if I combine A and B, and then I combine it with C, it's the same thing as if I had combined B and C first, and then combined the result of that with A. So this is a very special property of a binary operation, which is not satisfied by the operation that I wrote above. Okay, and if you want to draw a picture of this law, what it looks like is like this. A and B come together to produce A star B, and then this comes together with C. Okay, on the other hand, I could combine B and C first, and then combine the result with A. And the idea is that this diagram and that diagram are the same. So you could kind of imagine, just as a kind of movie, you could imagine that this line might attach at a point that's lower down, and it might slide over, and it might slide over to the other side, so that now it's attaching on this side. Okay, and you could imagine that the associative law is telling you that if you have a diagram like this, where this branch is attaching at this point, you can slide the attachment point over to the other side, to the other branch. Okay, let me give another example, just so that you start to see how these things are built up. Monoid. Okay, so a monoid, it's a magma, which is a semigroup, so it satisfies the associative law, but it has an additional piece of structure. It has an element in it, which is called the identity element. So it's a semigroup with an identity element. E is an element of A, and E star A is equal to A star E is equal to A for all A in A. So it has something that acts trivially when you multiply it against something. Okay, so for example, if we consider the integers with multiplication, okay, and the number 1, this is a monoid. Or if I consider the integers with the operation plus and the element 0, this is also a monoid. Okay. Okay, and before I take and I should say how to draw this picture. So the operation star can be written like this, like we did before, and the identity can be written like this, like a dot, which is inside. So in other words, if you read the diagram from top to bottom, it's like there's nothing, but all of a sudden we have an element inside the set. And the identity law can be written like this. So you could say, suppose that I take the product of something, you know, just imagine at the top of the picture, someone gives you an element of the set and it flows down, right? And if you then multiply the identity with that element, that's the same thing as just flowing and doing nothing, no multiplication. And that's the same thing as if you were to do it on the other side. Okay, so you could, again, as a movie, you could think that if you see a diagram like that, then what it means is that it takes as an input any element, okay, and then it multiplies it against the special element E. Okay, but you could think that actually when you see this little blob sticking out of your diagram, you can just like shrink it until it doesn't even exist anymore. That's what the identity law says. It says that these blobs, they're removable. Okay, and finally, the most important of this whole sequence is a group. So a group is a set with a binary associative multiplication. So this is a semigroup, but it has an identity element. So this is a monoid. So it satisfies both the associative and the identity laws. Okay, but it has an additional very nice operation, which is a unary operation. And it's called the inversion. And it takes any element to its inverse. Its inverse. So if you have any element of the group, G, then this is what we normally call, this is notation, G to the -1 is the inverse of G, i.e. G inverse, when I multiply it against G, I get the identity. And it doesn't matter which order I do it in. Okay, so a group has an additional property that every element has an inverse. Okay, and so that inverse is an additional, you can think of it as an additional operation on the group. And you can prove that if an element has an inverse, then that inverse is unique. You can show that the inverse is unique when it exists. Okay, but okay, and I should I can even go, let's go even further. So a special case of group, which we care about very much. We care, oh, and so what are these groups? So for example, we saw one already, the bijections of a set. Okay, that's a non-empty set of maps. It has composition. So two maps, when I compose them, I get another map from X to X. Oh, sorry, maybe before I wrote XX. So I don't need to double it. So I'll just call these bijections from X to itself. The operation, the binary operation is composition. The identity is the identity map on X. And the inverse is just inversion of the bijection, which you showed in the assignment exists, right? That every bijection will have an inverse. Okay, so this satisfies the laws of group. And so this is an example of a group. And note that this group is not commutative. So it's not true that that F composed G is G composed F in general. Okay, when the composition law, when the multiplication is commutative, we call G an abelian group. Okay, that's named after Abel. It's an actual person, a famous mathematician. Okay. So we can continue with these examples. We're going to do that on Thursday. Okay, the next example will be ring. And the next example after that will be field. Okay, but I want you to read the first chapter of Axler where fields are introduced. And then when you see it on Thursday, it won't be new to you. But I just wanted to demonstrate how we build up this algebraic structure bit by bit. We start with a set, we take a binary operation, we put some natural laws on the binary operation. We just keep building and adding more stuff into the set, and we build a hierarchy of mathematical structures. And this is how we build, the stuff of algebra. Okay, I'll leave it there, and I'll take a few minutes of questions.
Okay, so Lauren has a question.
Yeah. Hi, Professor.
Hi.
Let me see. I forgot the question.
We can come back
so,
to you.
Okay.
Okay, so Peng has a question in the meantime.
Hi, Professor.
Hi.
Just a quick question for the second and third like law for the equivalence relation and the
Oh,
second
back
and
to
third
equivalence
condition.
relation. Yeah, this is important,
Yes.
this equivalence relation stuff.
I didn't get why we need the x and y to be an element of s cross s and or like s cubed, not
I just
just
mean
s.
I just mean that you have a pair of elements, x and y. So I'm just saying that x and y are in S. That's all.
Okay, I see. Thank you.
Okay, so Lauren, did you figure out your question?
Yeah. So it's about the cycle.
Cycle.
So yeah. So
Okay.
so cycle is not only about map, but it is also about the specific elements in the set, right? So for each element in X, there might be a different cycle.
Yes.
Okay.
Yeah.
And
there could be several cycles. Like for example, here what we see is that there are 2 cycles. 1 and 2 together make 1 cycle, and 3 and 4 together make another cycle.
okay. And okay, so magma, semigroup, etc. They're all called algebraic structures, right?
Correct. They're all different algebraic structures, and you could study each one of them for years and years. They are like
right.
the fundamental building blocks of mathematics.
Okay. Thank you.
Okay, so Kai has a question.
Hi. I
Hi.
noticed that lecture 3 link and like 4 link were not posted on Quarkus. Are they going to be posted on Quarkus or?
What do you mean the link? What link to what?
So I mean the lecture 1 and lecture 2, there was a link on Quarkus.
Do you mean the Zoom link or the YouTube link?
A link to the Zoom recording, I think.
Okay. Maybe I forgot to put the lecture 3, you say? Lecture 3 and 4?
At least I believe that is the case.
Okay, yeah, I'll put them up.
Okay, thank you so
with
much.
today's lecture. What else? Why are there people entering the waiting room now? I don't understand. Why? For those people who just entered the waiting room or like entered the chat now, why are you doing it?
I think some people get disconnected, and so they want to reconnect and maybe
Okay.
hear people's questions.
Okay.
Yeah. Long Tai has a question.
Hello. I just
Hi.
want to know like what should we be reading like this week?
So the second assignment is out, and the reading assignment is on the second assignment.
All right. Thank you.
It's chapter 1. Should read about the read chapter 1 from the textbook.
Okay, so Shishu has a question. Shishuo.
Hello, Professor.
Hi.
I have a question about the cycle.
Okay, yeah.
So for the matrix expressions, why you write the one in the first row in the last position?
So when we have a cycle, that means that 1 is sent to 2, 2 is sent to 3, etc. K minus 1 is sent to K, and K is sent to 1. So that means that the last element of the domain is going to be sent to the first element. So that's why I have to put the 1 here, right? This tells me that the number K is sent to 1.
Okay.
The way you have to read these matrices, you need to get used to reading these matrices. This is like saying that you start here. 1 is sent to 2. 2 is sent to 3. 3 is sent to 4. That's how you have to read these.
Oh, yeah.
The matrix is designed to give you the information of what the numbers from 1 to k are sent to.
Okay, thank you.
Okay, next.
So Elliot has a question.
Hi, Professor.
Hi.
When we were looking at a matrix mapping from B sub m to B sub n, this was earlier.
Yep.
We had sort of right there at the bottom, the sort of final matrix.
Yep.
When you say that M1 plus dot 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 plus MK is equals M as a partition, do you mean that it's like literally partitioning like the number of ones, like M? Like,
So, yeah, I mean, you see here, you could think of it in several ways. I mean, what's really happening, right, is what we discussed last week, which is that the domain is being partitioned into subsets, which are pre-images, right? This is the pre-image of 1. This is the pre-image of 2, and this is the pre-image of 3. So the domain is being partitioned into 3 subsets. Each subset is a pre-image, right?
Yeah.
So, but if I look at the matrix, each column corresponds to a point in the domain, right? So the domain is being partitioned into, into these parts, right? And the size of each part is a number, M1, M2 up to MK. And I know that because this is a partition of the domain, the sum of these numbers must equal to the total cardinality of the domain. So we get a partition of the domain and a partition of the number, which is the cardinality of the domain. We get that number decomposed as a sum of smaller numbers.
yeah.
Does that answer your question?
Yeah. Okay. Thank you.
All right, so Omar has a question.
Hello.
Hi.
Yeah. About the quizzes that you mentioned we'll be having throughout the classes. When are they going to start?
They're going to start when they start.
Great. Question 2, will we...
I'm testing a software right now, so it's not quite ready, but hopefully it'll be ready soon.
I see. And I literally I had something to mention on Quarkus, but I forgot. Will we get solutions for the problem sets or no?
No, I'm not providing written solutions. You need to use the tutorials in order to help with the parts of the problems that you don't know how to do. So what you should do is when you get your assignment back and you see that some parts are problematic, then you should make sure that you get clarification on that, either by yourself, just working on your own, or asking the TAs about it.
Any expectation? Should we have any expectation for when we'll be receiving them or no?
Well, we have to check. I mean, the problem is right now we are still having this problem with this missing TA, but so it might be a little bit slower at the beginning than in the middle. But yeah, I mean, normally it should be coming back within 2 weeks. We'll see.
I see. Thank you.
It's difficult because sometimes the TAs have some kind of emergencies. There's a lot of people who are not able to. Yeah, anyway, it's complicated. Hopefully everything will run smoothly. Normally it does.
Okay, so Howard has a question.
Hi, Professor.
Hi, Howard. Go ahead.
So I have a question, just making sure I understand the cycle notation correctly. So if we permute the number inside the brackets of the cycle notation, we are producing like similar maps. Is that correct?
Yeah, so what Harold is asking is, so if I consider a different map, which looks like this, let's say I just permute 1, 2, 3, 4. Suppose that I map, I take 3, 4, 3, 3, 2, 1, 4. Okay.
Not across
Just
brackets.
one second. Just one second.
Sure.
So what have I done? So I've written a different map. This map takes 3 to 2, 2 to 3, and it takes 1 to 4 and 4 to 1. So this map and this map are different maps. You agree?
Yes.
Okay, they're obviously different maps. This one takes 1 to 2, this one takes 1 to 4. Okay, but they have the same shape. They have the same general shape, right? We have two objects which are being switched, and another two objects which are being switched. Okay, so the only thing that's different between this map, this map, and this map is the labeling of the elements. Okay, this should show you right away that these two maps are conjugate. They are similar, and even better, they're conjugate. So they are equivalent maps if we consider relabeling as the equivalence relation, right? So for example, what is the relabeling? Well, it's just 1 is relabeled by 3, 2 by 2, 3 by 1, and 4 by 4. So if you relabel 1 as 3 and you relabel 3 as 1, then the map is exactly given by this notation. So you can see the power of the cycle notation, right? Because it's the shape of the notation which tells you the equivalence class of the map, right? As long as it has this shape, then you know that the map will be similar or conjugate. That's typically the way that, that's the way that these notations are developed. The notation is developed in a way so that the classification of the map is visible by the shape of the notation.
All right, thank you.
You're welcome.
Okay, so Jay has a question.
Hi. So I guess I can kind of go back to Howard's question sort of in the same way, but I mean, just, or is it the example that we're using? So when we had, so there was 3 sort of equivalence relations. There was the reflexive, symmetric, and transitive.
Sorry,
So,
no,
oh,
no. This is very important.
Okay.
It satisfies all these. Everything must hold.
Everything must hold, right?
It must be reflexive, it must be symmetric, and it must be transitive.
Okay.
So for example, okay, there is a relation that you know very well, which is a relation on numbers, which is greater than. X is greater than Y. What does it satisfy? Does it satisfy transitivity?
Yes.
That's a question, not an answer, even though you said an answer word. If X is greater than Y and Y is greater than Z, is it true that X is greater than Z?
Yes.
Yeah, so transitivity holds. If
Okay.
X is greater than Y, does it mean that Y is greater than X? No, so this fails, and X is greater than X also fails. So greater than is not an equivalence relation.
Okay.
Because it does not satisfy all 3. Greater than or equal to
does.
Howard is shaking his head. Why does it not satisfy? Why is it not an equivalence relation?
Right, so, oh, wait, so then.
I'm asking Howard. He was the one shaking his head.
Sorry, I didn't say.
I think it's still not satisfying the symmetric.
So if X is greater than or equal to Y, does it follow that Y is greater than or equal to X?
Not necessarily, I think.
Not necessarily, because X could really be bigger
Yeah.
than Y. And then Y is not greater than, or, 3 is greater than or equal to 2, but 2 is not greater than or equal to 3. So greater than or equal to satisfies the reflexive and the transitive, but does not satisfy symmetric. Equality of numbers, thankfully, is an equivalence relation. I mean, otherwise it would have no business of being called an equality, right? And any relation which partitions the set that it's defined on is an equivalence relation. So, for example, being of the same species is an equivalence relation. It divides all living things into species. If the biologists did their partitioning correctly, then it should be an equivalence relation. Okay. Or, being the same type of car, the same company of manufacture of car is an equivalence relation. Anything that divides, that has a clear division of a set into a partition of subsets is giving you an equivalence relation. Is that enough? It doesn't look like, it looks like you might still have a question.
Yeah, no, oh yeah, no, mine was concerned with the sets, but how the equivalence relation. So when we're essentially, so it's partitioning a set, it's essentially when we have this equivalence relation.
Yeah.
Okay.
Yeah, so here we see it that, where is it? Here. We have a set of maps, okay? And we wanted to partition the set of maps into ones that are similar to each other, right? These are similar to each other, and these are similar to each other. So we have a partition into two subsets, one of size 3, one of size 6. Okay, so it's a good way of partitioning or classifying certain subsets. We should say that this is one species of map, and this is another species of map. They're two completely separate species of maps. And note that this is the same species as this. Don't be fooled by the fact that they cross here. The fact that they cross is not a true fact about the map, because I can just relabel.
Right.
I can just relabel it, and then it won't be crossing. Okay, let's leave it at that. Do we have any? Is it desperate questions? Diana, do you want to ask your question?
Yeah, I think it's a short one.
Yeah.
Like, I think I misunderstood like one part. Like, yeah, we have the matrix with K. It's like a cycle, right?
Yeah.
I don't really see how it can be connected to a cycle like that we saw like on the last page with the like where we had like 1, 4 and like
Yes.
2, 3, or it's like the page after. It's like, yeah, this one, like the blue thingy. Like, how is it connected to the matrix? No,
okay.
like
So
the blue line. Like, okay.
So let's say that you have suppose that this was your permutation. This is a permutation that cyclically permutes 1, 2, and 3, cyclically permutes 4, 5, and 6, and then switches 7 and 8. That's what this map does.
But like, what if it's
Just
like
one
not
second.
by
Just one
order?
second.
Okay.
Just 1 second. So if this is your map F, then the question is, what is the matrix of F? Okay. So I'm going to write it like this. So sorry, I just need a bit more space. So 1 is sent to 2. 2 is sent to 3. and 3 is sent to 1. Okay, this is one block. Then 4 is sent to 5, 5 is sent to 6, and 6 is sent to 1. That's another block. And then 7 and 8 are switched. So 7 is sent to 8, and 8 is sent to 7. Everything else, 0. Okay, so what you see is 3 blocks, each of them looking like this standard block. Just a small one. This is one that's small. It's k is equal to 3, k is equal to 3, and k is equal to 2. So we have 3 cycles making up the map.
Okay.
Does that help?
Yeah. Yeah.
But this is a big 8 by 8 matrix. You should just, it's all zeros here. 0, 0, 0, 0, 0.
I was just wondering if it's not by order, but then it's doesn't make sense. Yeah.
So yeah, I mean, you have to be careful that the order here is the same as the order above. So if 1 is sent to 2, you have no choice. 1 is sent to 2. 2 is sent to 3, and so on.
Okay. Thank you.
Chinyuan, you want to go ahead?
Yeah. Hi, Professor.
Hi.
I have a kind of basic or
just go ahead. Just ask. Just ask the question.
I wonder how the classification by relabeling and codomain and domain can help us to learn math. I'm not so sure what can classification of maps do. That is my question.
Well, I mean, a large part of mathematics is about classifying structures.
Yes.
And here's a simple example, right? That there's many maps, and the question is, are they all totally separate? Are they all completely unrelated? Are they in any way similar? And you can see that, just intuitively, that these are much more similar than these, right? So in other words, there's plenty of cases, there's many, many cases where we have an intuition that certain things are of a different type and that we want to classify them in different ways. But the question is, what is the exact mathematical meaning of that? The exact meaning is that we need to figure out how to define an equivalence relation on the set that we're interested in such a way that it partitions it into subsets which are considered to be equivalent. So for example, you might have a lot of data. This is you might have some kind of data which appears in this format. It may present itself to you in this way. And you might look at all this data and think, well, intuitively speaking, it seems to be classified into 2 types. There's the diffuse type, and then there's this concentrated type.
Yeah.
So you make this conceptual leap where you classify all these as one type of object, and you classify all these as one type of object. So you might be able to classify these as, one type of customer, and this is another type of customer. So it's very useful to know when a customer comes in, which type are they more likely to be, right? So you would like to have a classification of your customers. So how do you do that? Well, you need to come up with a definition of an equivalence relation in order to partition them into different sets. And the question is, how do you do that? You cannot expect to be able to visualize and to be able to stare at it and just basically decide in a human way this is one group and this is another group. You might need to have some kind of algebraic way of systematically classifying things, right? And that's an example. This is an example that I presented to you, a systematic classification of these data, which made these 3 equivalent and made these 6 equivalent.
I see.
Okay? So that's one of the most important functions of mathematics, is to be able to take a very complicated set and to partition it into understandable species.
I see. So
And
relabeling.
the main tool of that conceptual tool is an equivalence relation. But the way of constructing the equivalence relation, there's many different techniques of doing that. And we're going to see in linear algebra a version of this relabeling technique, which allows us to show that linear operators are similar. Okay, I'm going to leave it there. Everyone have a good middle of your week. I'll see you on Thursday.